Good evening, everybody. This is the April 18th, 2019 meeting of the local New York ARS chapter up at CCNY in Shepherd Hall. Tonight we have a returning host who is no stranger.
I'm the guest. You're the host.
Oh, I'm the host, that's
Yeah,
right.
you're the
returning guest who is no stranger. Hello, Bob, how are you? A returning guest to give a very interesting paper, Gary Galo, and the title of his paper is RIAA Equalization for Velocity-Sensitive and Displacement-Sensitive Phono Cartridges. Boy, you got a lot to explain for yourself tonight with that title. Let me just give a little background on what he's going to talk about. The RIAA recording and playback curves are quite familiar to audio engineers, record collectors, and audiophiles. The recording curve shows a bass cut and a high-frequency boost. The playback curve provides a complementary frequency characteristic, resulting in what is called a flat response. Most people think of the recording curve as a representation of recorded amplitude, sometimes called quote-unquote displacement, but it's not. The vinyl record is cut with a hybrid of constant displacement and constant velocity recording characteristics. This presentation will examine both types of cutting, the frequency response of the record itself, and the response produced by playing the record with velocity-sensitive cartridges, specifically magnetic types, and displacement-sensitive cartridges, examining some of the misleading statements made by manufacturers of strain gauge types. Gary Galo, let me just give you a little background on him, because he really does not need any introduction, but he really deserves a very good introduction for everything he has done. And it will be self-evident from the short bio I'm going to read. Gary A. Galo retired in 2014 after 38 years. He should have gotten a Purple Heart for that. As audio engineer at the Crane School of Music, SUNY at Potsdam, New York, where he also taught courses in audio technology and music literature. He now works as a volunteer in the Crane Recording Archive doing preservation, restoration, and digital transfer of vintage Crane recordings. He is also a Crane alumnus, having received a BM in music education in 1973 and an MA in music history and literature in 1974. Gary is a widely published author with more than 300 articles and reviews in both musical and technical subjects, and in over a dozen publications. He has been an active member of the Associated Recorded Sound Collection since 1989 and a frequent recording and book reviewer for the ARSC Journal. He has given numerous presentations at ARSC annual conferences, many of which have been published in the ARSC Journal, and has been a regular presenter at ARSC New York chapter meetings over the past few years. He was the sound recording review editor of the journal from 1995 to 2012, and co-chair, with yours truly, thank you, of the ARSC Technical Committee from 1996 to 2014. He has written for Audio Express magazine and its predecessor since the early 1980s. He has also published numerous book reviews and notes, Quarterly Journal of the Music Library Association, has written for the newsletter of the Wilhelm Furtwängler Society of America, Toccata, Journal of the Leopold Stokowski Society, and is also author of the loudspeaker entry in the Encyclopedia of Recorded Sound. He has written several articles for linear audio, as well as being a member of the Audio Engineering Society and Societe Wilhelm Furtwängler. Without further ado, I want to introduce one of our regular guests, who really doesn't need an introduction, but he did, but I wanted to do it anyway. Mr. Gary A. Galo. I think it's going to be quite an evening.
Thank you. Thank you, sir. That was way too long. I'll shorten it next time. Well, thank you all for coming. Does everybody have a handout? There is a handout up there on the music stand. The handout is just a rather lengthy list of references that I have used related to this subject. We're going to cover a lot of material in the next hour and 15 minutes, and the slideshow is pretty comprehensive. And if anyone would like a copy of the handout or the slideshow as PDF files, please drop me an email. And that way you can just click on the links in the handout rather than typing all those references in. I checked all of the links on the handout within the past 3 weeks, and they all worked at least 3 weeks ago. And I would also be happy to send PDFs of any of my own articles on this subject that I've listed at the beginning of the handout. What I'm going to talk about early on in this presentation will be familiar to a lot of you, and if it's review and you already know all of this, just bear with me. It'll get us all on the same page as far as terminology is concerned. But then when I move into the somewhat unfamiliar area of displacement-sensitive cartridges, I'm pretty sure that this will not be review for most of you, and it might be either new material or material that you really haven't thought about in quite a long time because there hasn't really been any need to. So, these are the familiar RIAA recording and playback curves, and the recording curve shows a bass cut and a treble boost, that's the blue line, and the play curve shows a complementary bass boost and treble cut. And the result, of course, is the flat response that's shown in black across the center of the graph. But just exactly what does the recording curve represent? This is what's often misunderstood about phono equalization. And the other thing is that this playback curve applies only to one type of phono cartridge. Now, there are two ways to cut a phonograph record. One is constant, and we'll look at both of them in more detail shortly. And the two ways to cut a phonograph record are basically constant displacement and constant velocity. And there are also two main types of phonograph cartridges. There are velocity-sensitive cartridges, and these are all magnetic types. And that includes moving magnet, which are most common, moving coil, and moving iron. And there are also those which are displacement sensitive, and the most common are crystal and ceramic types, which are basically the same thing, and strain gauge cartridges, of which there's been kind of a revival in interest in recent years, and we'll get to that later on. There are also electret cartridges and LED cartridges. Both of those are pretty rare, but we'll also get to them later on in the presentation as well. Let's look at the concept behind the two types of disc cutting that I mentioned in the previous slide. Constant displacement is pretty straightforward. The disc cutter produces a groove of equal displacement from the low frequencies to the high frequencies. In other words, if the signal level fed to the cutter is at a constant level with rising frequency, the cutting and playback stylet will be displaced physically by an equal amount in the bass region and the treble region. Now, this is sometimes called constant amplitude cutting, and that's fine, but engineers, I find, tend to find displacement to be a more technically descriptive term, so I'm going to use displacement throughout most of this discussion. I used the term constant amplitude back in my old 1996 paper on disc recording EQ, but I've come to find that people like displacement a little better, but they can be used interchangeably as far as I'm concerned. The problem with constant displacement cutting is that it can produce a treble region that's impossible for any phono cartridge to track. And if you feed too much voltage to a magnetic cutter at high frequencies, you'll burn up the cutter. And there are more than a few cutting engineers that have learned that the hard way by trying to cut too high a level at high frequencies, burning up expensive cutter heads. Now, there are crystal cutters that do have a constant displacement characteristic, but they have limited frequency response and lower overall cutting levels and higher distortion than magnetic cutters, and they're not suitable for high fidelity applications. But they do exist, and they particularly were used on home recording equipment a long, long time ago. Now, one really important point before we move on to the next slide. With constant displacement cutting, the recorded velocity rises at the rate of 6 dB per octave as we move up the frequency spectrum. Now, in order to understand constant velocity cutting, we first need to define the term velocity as it relates to disc cutting. It simply refers to the speed at which the recording or the playback stylus travels, and it's related to the physical distance that the stylus travels in any given time period. Now, in order for the stylus to travel the same physical distance as the frequency rises, the displacement or amplitude has to drop at a rate of 6 dB per octave. And you can see here that every time the frequency doubles, going from this one to the smaller one in the center, every time the frequency doubles, the displacement is cut in half. The problem with constant velocity cutting is that at high frequencies, they're too low in level, often below the surface noise on the record. And the other problem is that if the displacement in the bass region is too high, the cartridge won't be able to track the record in playback. Now, as I mentioned earlier that we can divide phono cartridges into two broad categories, velocity sensitive and displacement sensitive. So let's look at how each responds to the two types of disc cutting that we just looked at. Here is the constant displacement recording characteristic. And if this type of recording is played with a displacement sensitive cartridge, the cartridge output will be flat across the frequency spectrum. And that's what's shown with the blue line here. But if you play this record with a velocity sensitive cartridge, the cartridge output will rise 6 dB per octave with frequency. And that's shown by the red line. This is how all magnetic cartridges work. Magnetic cartridges are velocity sensitive devices. They're velocity sensitive transducers because they convert mechanical energy back into electricity. Here is the constant velocity recording characteristic. Now, if this type of recording is played back with a velocity-sensitive cartridge, like a magnetic cartridge, the response will be flat across the frequency spectrum, like you see in the red line. But if this record's played back with a displacement-sensitive cartridge, the response will fall at 6 dB per octave from the low frequencies to the high frequencies, as we can see with the blue line. So which type of cutting is best? Well, electrical recording was introduced commercially in 1925, and its inventors, Maxfield and Harrison, who worked for Western Electric, realized that the best approach was a hybrid of these two systems. Now, back then, most disc record speeds were in the ballpark of 78 RPM, but rarely at exactly that speed. But like Alton Brown says in Good Eats, that's another show that we won't get into tonight, and is only peripherally related to what I'm talking about. Now, this is the recording characteristic that was used for the earliest electrical recordings. The low frequencies are cut basically with a constant displacement characteristic, and the high frequencies are cut constant velocity. And the transition from one to the other is called the bass turnover frequency. And it was usually in the 200 to 300 hertz region on the earliest electrical recordings. On some early electrics, it was even lower than that, sometimes as low as 150 hertz. What constant displacement does is it limits the groove excursions at low frequencies, and constant velocity does the same thing at high frequencies by attenuating the highs. And this made the record playable on contemporary playback equipment, including acoustic phonographs. We have to remember that the earliest electrical recordings, when they were introduced, most people had acoustic phonographs to play them on. And Victor even bought the rights to a Western Electric machine, which they called the orthophonic Victrola, which was an acoustic phonograph specifically designed to play electrical recordings. But they had very heavy tracking forces, like all acoustical phonographs. So they had to be able to make a record that would play without wearing out prematurely on acoustic playback equipment. The frequency response of the earliest electrical recordings was limited to about 6 kilohertz in the treble, and there wasn't usually much below 80 to 100 hertz on the low end. Now here's that early electrical recording characteristic again. Now the solid line on the bottom shows recorded velocity. You can see during the constant displacement portion of the curve, the velocity rises. And then in the constant velocity portion of the curve, the velocity is flat or constant. The dashed line shows the required complementary playback equalization, and the dotted line across the center shows the flat result. Now, as the high frequency response of records began to improve, record surface noise became more and more of a problem, and the solution was to revert back to a constant displacement characteristic in the higher frequencies. This was sometimes called treble preemphasis. Now, preemphasis implies a boost of some sort, and it is, but again, this is another misunderstood concept. It's a boost in recorded velocity, It's not a boost in amplitude. So rather than letting that constant velocity characteristic continue to the highest frequencies with the amplitude dropping all the way to the top of the spectrum, we stop that drop in displacement at a certain point, and then we go back to constant displacement. Now, the base turnover frequencies, well, the new transition point from constant velocity back to constant displacement is now called the treble transition frequency, and it was usually on the earliest electrical recordings in the region of 6 to 7 kilohertz. Later it was moved lower. And the base turnover frequency was gradually moved upward by most record companies from 300 to 500 hertz, sometimes even higher. And both of these varied from one record company to the next, and even from one recording session to the next. There weren't any standards back then. Now, the constant velocity region is really a region of transition between the relatively high displacement in the low frequencies and the lower displacement in the high frequencies. That's the whole purpose now of that constant velocity region, is to provide that region of transition between the higher cutting level down here and the lower cutting levels up here. And once again, the solid line shows recorded velocity and the response of a magnetic cartridge, of course. And the dashed line shows the complementary playback equalization, and the dotted line across the center shows the flat result. Now, in 1948, Columbia introduced the modern long-playing record. And along with the LP, there came a third transition point, which we call the low bass turnover. And this was done to reduce rumble from both turntables and the record itself by shelving that rise in response, that we need in playback at some predetermined low frequency. Now, the recording equalization curves, they were, as you know, were all over the place until 1956, when the Recording Industry Association of America adopted the curve that RCA Victor had been using. RCA Victor called their curve the new orthophonic curve, and that's the curve that eventually was adopted by RIAA, replacing the old Columbia curve. That curve became known as the RIAA curve, and it's been in worldwide use ever since. The recording characteristic is constant velocity up to the low bass turnover, constant displacement to the bass turnover, constant velocity from there to the treble transition, and then constant displacement from there to the top of the spectrum. Now, just like before, the solid line shows recorded velocity and the response of a magnetic cartridge. And the dashed line shows the required playback equalization, and the dotted line across the center again shows the flat result. Now, to improve the accuracy of the filter networks that are used to generate the recording and the playback curves, RIAA defined the curves by its time constants rather than by the turnover frequencies. Now, the formulas used to design filters for both recording and playback normally they require time constants, and you'll get a much more accurate result if you begin with time constants directly rather than changing frequency to time constant first. In 1979, someone I know some of you will be familiar with, some of you may even know him. In 1979, Stanley Lipschitz, who was a mathematician on the faculty of the University of Waterloo in Ontario, who's now retired, and a guy who used to be a staple of AES conventions many years ago, Stanley Lipschitz in 1979 published a landmark paper in the Audio Engineering Society journal called On RIAA Equalization Networks. And he named the three time constants T3, T4, and T5. T3 being the low bass turnover, T4 being the bass turnover, and T5 being the treble transition point. And they correspond, of course, to transition frequencies, which are labeled F3, F4, and F5. And the numbers here are going to be familiar to most of you. The low bass turnover point is 50.05 hertz. The bass turnover is 500.5, and the treble transition is at 2122. Now, If you're not familiar with the Lipschitz paper, you're probably wondering why he started with T3. What happened to T1 and T2? Well, let's start with T2. T2 is a low-frequency playback roll-off that was proposed by the IEC back in the 1970s as an amendment to the RIAA curve. And what the IEC proposed was an additional turnover at the bottom of the spectrum, 20 hertz, that basically made a high-pass filter cornering at 20 hertz. So the 3 dB point for that filter at 20 hertz was what the IEC recommended as a playback supplement to the RIAA playback curve. It never gained any favor with audiophiles or professionals because the degradation in the bass was always audible on wideband systems, and the IEC recommendation was finally withdrawn sometime in the 2000s. No one ever took it very seriously. I tried it once in one of my own phono preamps, and I could hear the effect of it and decided, nope, no good, and they finally withdrew it. T1, and there's also a T6. T1 and T6 are additional time constants that come into play with certain types of feedback-based RIAA equalization networks. They are well beyond the scope of the subject of this presentation. You can read the Lipschitz paper, and he explains all of it in almost excruciating mathematical detail, but he goes into it in very thoroughly. Now, I don't intend to get into the actual design of RIAA playback equalization networks for magnetic cartridges. That's really outside the scope of what I'm covering today, but I would like to make one point. And that is that RIAA equalization networks for velocity-sensitive cartridges, in other words, magnetic cartridges, they are a series of low-pass filters and shelves. And with the low end of the frequency spectrum as our reference, we have a low-pass filter at T3, which creates the shelf below that point. We have a shelf at T4, and we have another low-pass filter at T5, okay? And that creates the required, and that then determines the required playback response, or creates the required playback response. And if you're knowledgeable about filter terminology, you know that we can say that we have a pole at T3, we have a 0 at T4, and we have a pole at T5. If you're not familiar with that terminology, you don't really need to worry about it to get the gist of what we're talking about tonight. Now, even if you're designing an equalization network to play 78s, where the low bass turnover was never defined or implemented, you still need to have a low bass shelf in playback. You can't continue that low frequency boost down to DC. You simply can't do it. So you have to create it in playback. And even though none was specified as part of the recording curve, and vintage records tend to have limited low frequency response anyway, and record companies didn't worry too much about what went on in the bottom 2 octaves of the spectrum because there basically wasn't anything down there except noise. So we need to shelve the response in playback. My rule of thumb in designing playback equalization networks for vintage records is to maintain a 10-to-1 ratio between the bass turnover and this low bass shelf, which you have to put in. So if your bass turnover is 300 hertz, the low bass shelf is at 30 hertz. And no one will ever hear it on an old record with, in fact, the effect you will hear is that the records will play back with a lot less rumble. It's actually not only necessary, but it's basically a good idea. All right, that brings us back to the familiar graph of the RIAA record and playback curves. And by now, it should be clear exactly what the record curve represents. Again, that blue line here that shows the bass roll-off and the treble boost. What the record curve represents is recorded velocity. It doesn't become a graph of amplitude until the cartridge is played back with a magnetic phono cartridge because the magnetic cartridge is velocity sensitive. And it's the response of the playback cartridge that determines the required playback equalization. And the playback curve is what it is because the vast majority of phono preamps are designed to accommodate magnetic cartridges. And that's a very important point. Now moving on to some probably less familiar territory. There are also displacement-sensitive phono cartridges, and their output is directly proportional to recorded displacement or recorded amplitude, if you prefer to think of it that way. For a displacement-sensitive phono cartridge, the solid line across the top here is now the RIAA curve. The cartridge output is highest below the base turnover. It flattens out in the region between the low base turnover and the base turnover, drops between the base turnover and treble transition, and then flattens out in the upper constant displacement portion of the curve. Now, since the region between T4 and T5 with RIAA cutting is just over 2 octaves, it stands to reason that the difference in level between the bass region and the treble region should be just a little over 12 dB. Remember that we're dealing with a little over a 2 octave spread between 2122 and 500.5, and at 6 dB per octave stands to reason that a little over 12 dB would be the level difference between the bass and treble portions of the curve. Now, the required playback response is shown by the dashed line. And with the upper end of the frequency spectrum as our reference, the response is flat down to the treble transition frequency. It drops at 6 dB per octave down to the bass turnover, is flat to the low bass turnover, and then drops at 16 dB per octave below that point. Now, you remember just a few slides ago that an RIAA equalization network for velocity-sensitive cartridges was a series of low-pass filters and shelves. Well, an RIAA equalization network for a displacement-sensitive cartridge is just the opposite. It's a series of high-pass filters and shelves. And with the upper end of the frequency spectrum as a reference, we have a high-pass filter at T5, which creates a shelf above that point. And then we have another shelf at T4, another high-pass filter at T3, which creates this shelf. And then the high-pass filter creates a roll-off below the T3 low bass turnover point. And again, if you're knowledgeable about filter terminology, you can say that there's a pole at T5, there's a 0 at T4, and another pole at T3. But again, if poles and zeros are a little confusing, you don't need to worry about that too much for tonight. So which cartridges are displacement sensitive? Well, the most common are crystal cartridges, which use a piezoelectric element that generates a voltage when it's twisted. The term piezo implies applying some kind of stress. And a piezoelectric element generates a voltage if you flex it or stress it. And that's what crystals, or ceramic crystals in the case of ceramic cartridges, that's what they do. Again, ceramic cartridges are nothing more than a variation on crystal cartridges. They basically work the same way. And they were most common in cheap portable record players, and they featured, if you will, a flip-over stylus that had 33 1/3 on one side and 78 RPM on the other side. And they had very high tracking forces, and I think most would agree they were equally adept at destroying both types of records. Now, there were equalization networks for crystal cartridges, and they can help us understand the equalization requirements for high-end displacement-sensitive cartridges, which I'll get to a little bit later. And there are two very old sources that can help us unravel this mystery of how to do this. The first is Howard M. Tremaine's Audio Cyclopedia. Now, this book was already obsolete when the final edition appeared in 1969, and people who were not sensitive to historical matters or not interested often criticized it for that. But Tremaine's Audio Cyclopedia is a goldmine of technical information on the historical aspects of audio, and anybody interested in the history of audio technology needs to have this on their shelf, because you'll refer to it time and time again when you're researching historical topics. There's a much older source called the Radiotron Designer's Handbook, which was edited by Fritz Langford Smith, and this one Like Tremaine, he devotes an entire chapter to what he calls reproduction from records, and it's well worth reading by anyone interested in older disc playback technology, including older playback curves. This fourth edition, 1952-53, is the one that you want. The earlier editions don't have nearly as much information related to what we're talking about tonight. So what you want to do is find the fourth edition. Fortunately, it has been scanned and reprinted and issued on a CD-ROM, and the place where you can buy it is listed in that handout and the list of references. Now, Howard Tremaine published this network for equalizing crystal cartridges, and the two capacitors that you see up here allow varying the treble transition frequency, and the large value resistors in the low end provide switchable rumble filtering, which also compromises the low frequency reproduction. The formulas you don't need to get bent out of shape on, and I don't expect you to remember them when I go to the next slide, but again, I'll send you this whole slideshow as a PDF file, and you can go back and take a look at the math yourself. But basically, T4 is the product of R1 and C1, and T5 is the parallel combination of the two resistors multiplied times C1. Now, remember that the bass turnover T4 and the treble transition T5 are just over 2 octaves apart. So logic would dictate that the region above T5 should be a little over 12 dB higher in level than the region below T4. Now, I ran a simulation on this circuit, and the graph shows the result. And curve A, which is the lower curve, it uses the parts values that were given by Tremaine. And the level difference in curve A is between the bass and treble regions is about 14 dB, which seems a bit excessive. So I recalculated the filter values to match the RIAA time constants, and that simulation is what's shown in curve B. And now the difference between the bass and treble regions is about 12.5 dB, which seems much more reasonable, okay? And you can see the values that I used and the values that Tremaine used to produce those two curves. But you're probably wondering, what happened to T3? Did Tremaine forget about it? Well, no, actually he didn't forget about it at all. It turns out that crystal cartridges have an internal capacitance, which is usually between 1 and 1.5 nanofarads. And what we need to do is add that capacitance to our simulation. And that's C2 here, which I have added to simulate the internal capacitance of the cartridge. And it turns out that 1.528 nanofarads is the optimum value for the RIAA curve. So here we have a simulation with the cartridge capacitance added, which I rounded off to 1.5 nanofarads, which is a convenient off-the-shelf value. And curve B this time is with the RIAA values that I calculated, and curve A is with Tremaine's. And now I think we're really onto something here. Again, Tremaine shows a bit lower level, or a bit, I guess, a bit higher difference between the bass and treble portions of the curve. And B, I think, is, with my own values, is much closer to the mark. But now I think we're really on to basically understanding how equalization for displacement-sensitive cartridges should work. Now, what Tremaine had was a high-impedance network that was designed for tube amplification. And what I did was a phono equalizer with low-impedance networks that are suitable for op-amps or other solid-state circuits. And I've configured both of these op-amps as inverting amplifiers. And this circuit uses isolated networks, the first one for T3, and then the second one for T4 and T5. And putting T3 first provides some rumble filtering at the outset, which prevents overload of the op-amp stages that come a little bit later on. Now, the isolated networks produce a much more accurate playback curve. In a composite network, there are interactions which affect frequency, and in order to make them work ideally, you would really need another Stanley Lipschitz style article on designing RIAA networks for displacement-sensitive cartridges. And given the limited interest in this subject, I doubt that anybody's going to do that. The whole reason for the Stanley Lipschitz article is because of the unwanted interaction in composite RIAA networks. A composite RIAA network has 2 capacitors and 2 resistors. So you have 4 different RC combinations that yield 4 different time constants. We only want 3 of them, and that's the problem. The unwanted 4th one is what causes an interaction that throws the other values off. And you don't have this problem with isolated networks. Stanley Lipschitz's real contribution to this field is that he provided the math for designing extremely accurate composite networks. And again, the details of all that are another show. He also provided the math for designing networks in feedback-based circuits that require an additional resistor for amplifier stability, which is a topic that's way beyond what I'm going to get into tonight, but his paper explains all that. It's a rather complicated subject. So basically what we have here in my own isolated networks is we have 2 curves. We have curve A with the ideal values that I show here, and B is comparing it to Tremaine's original circuit. And again, you can see, again, Tremaine's original circuit has roll-off that's a bit excessive, or I should say a level difference between the treble and bass regions that is a bit excessive. Now, let me just take a sip of my water here if I can find it.
It's on the podium.
It's on the podium.
Right there.
You moved it,
Yeah.
so I couldn't find it. Now, there are displacement-sensitive cartridges that are suitable for high-performance audio, which clearly crystalline ceramic types normally are not. The most common is the strain gauge type, and back in the 1970s, there were strain gauge cartridges that were made by Win Labs. A gentleman by the name of Sao Win, who still lives in California, designed and built these. I attempted to contact him a couple of times during the course of my research on this subject and never had any luck. But this is the Win Labs SDT-10-2 strain gauge cartridge. Now, like most strain gauge cartridges, these used a piezo-resistive element. Again, piezo implies applying some kind of stress, and piezo-resistive means that when you apply stress to it, to this element, its resistance changes. It doesn't generate a voltage on its own like a piezoelectric element does, but its resistance will change. And in these cartridges, it's a semiconductor element, a piezo-resistive semiconductor that changed resistance as stress was applied, or as the stylus moving back and forth twisted the element. Now, the story with the Win Labs cartridges, and you can still read this stuff on the internet, is that they didn't require any RIAA equalization. Well, in view of what we've just seen, this seems a bit strange. Panasonic also made strain gauge cartridges, and there's a posting on the internet by Sao Win where he says that Panasonic bought the rights to make his designs. But Panasonic also received a patent on their own strain gauge cartridge design, and I found that patent on the internet. I have a link to it in the handout. This is the Panasonic EP450C-2, which was made around 1976. Now, this is kind of interesting. Panasonic made a very elaborate preamp equalizer for their cartridges, and I was lucky enough to track down a schematic for the equalizer a few years ago. This equalizer is preceded by a flat stage with a gain of 22.5 dB. All right, the network at the input, which looks like the Tremaine circuit, the network at the input contains the T4, T5 filter. And basically what I've done is I've shown the various points along this circuit and the frequency response that appears in my circuit simulation at each of these points. So the T4, T5 filter is followed by an op-amp stage with a flat frequency response with a gain of 34.2 dB if you do the math. And the curve at letter A represents the T4, T5 response created by this filter and the gain of the amplifier. Okay? Now, the difference between the bass and treble regions in this circuit is less than 10 dB rather than the 12.5 dB that I would expect. The values they used in this filter, if you go through the math, they actually produce an F4 of 530.5 hertz, which is an oddball frequency, and an F5 of 1591.5 hertz. Now, 1590 hertz was the frequency used by NAB and Columbia for the original Columbia LP, but I'm sure that that's pure coincidence. What this is telling me, and what we'll see from the rest of this circuit, is that this cartridge did not really have an ideal displacement sensitive characteristic. It was off for whatever reasons. And related to that point, at letter B, we see the effect of a lower mid-range correction, which pulls the lower mid-range down. So this is a response at curve B. And then C shows the response of the T3 network. It's simply a coupling capacitor with a load. They show some of these resistors. They show fixed resistors in the schematics, and they label them as pot or potentiometer, which implies that those fixed resistors were adjustable. So it implies that they put a pot in there, but they didn't actually use the schematic symbol for a potentiometer. I have simply reproduced their schematic as they drew it. Okay? So C shows the response of the T3 filter, and that's what we see down here in the lower graph. And you can see the bass is now below the low bass turnover is rolled off, the response of that mid-range correction. And you can see the level difference between the treble and bass portions of the curve. Now, in the Panasonic patent, there is a frequency response graph for their cartridge that shows that the cartridge itself has a rise in response above 10 kilohertz. And at letter D, you can see the effect of a low-pass filter that basically compensates for it. And finally, letter E shows the overall response with a 47K load, which basically drops the overall level of that curve we see at letter D, drops the overall level by about 6 dB. Now, it should be pretty obvious that the Panasonic strain gauge cartridges did not have an ideal displacement sensitive characteristic. This rather elaborate equalizer was their attempt to correct those deviations, and these deviations could have been due to electrical reasons, or it could have been due to mechanical limitations, and it was perhaps a combination of the two. And here's something I'm going to get to again shortly, that rise above 10 kilohertz in the Panasonic cartridge that they show in their patent, it may be due to the piezo-resistive semiconductor element's internal capacitance. I'll come back to that fairly shortly. Today there is a company up in Peekskill called Soundsmith that makes a line of strain gauge cartridges, and they claim that since their cartridges are displacement sensitive, they don't require any RIAA equalization. Okay, before I go any further, I need to point out that I am not making any qualitative statements about any of these phono cartridges, except the crystal and ceramic cartridges, which everyone agrees are kind of low end. But all of these high-end cartridges, I'm not making any qualitative statements about them. The Soundsmith cartridges have received rave reviews in the high-end audio press and may very well be the greatest phono cartridges in the world. What I'm trying to do here is figure out how things work. I'm not making any statements about how well they work, okay? So just bear that in mind. Now, 3 years ago, I wrote an article for Linear Audio on RIAA equalization for displacement-sensitive phono cartridges, and I examined the claims made by Soundsmith regarding equalization. And in fact, their claims regarding equalization and the lack of any need for it are what prompted me to begin this investigation in the first place. When I was working on the Linear Audio article, I contacted the owner and designer, Peter Lederman, and told him what my findings were on equalization for displacement-sensitive cartridges. And in particular, I noted the 12.5 dB difference in level between the bass and treble regions. He told me that if their cartridges were equalized as I suggested, they would be absolutely unlistenable and unsellable. Well, I sent several follow-up emails specifically asking how their displacement-sensitive cartridges maintain a flat response in the constant velocity portions of the curve, but I never got an answer. Now, Soundsmith on their website has an explanation of RIAA equalization that I find problematic, to say the least. They say that the RIAA curve cuts a groove of equal displacement. As we've seen so far, that is simply not true. If an RIAA record was cut a groove of equal displacement, the RIAA curve would not be a curve at all. It would be a straight diagonal line from 20 hertz to 20 kilohertz. You can't cut a groove of equal displacement across the entire audio spectrum with a magnetic cutting head. Now, John Ergel pointed out decades ago in his excellent book, Sound Recording, that cutting the high frequencies at the same level as the low frequencies would take an electrical toll on the cutter head that would be intolerable. In other words, you would burn up the cutter. And even if you didn't, the record would be unplayable by any known phono cartridge, okay? Now, as I've alluded to earlier, there are plenty of cutting engineers that even with RIAA equalization have burned up cutter heads trying to cut high frequencies at too high a level. Now, later in Soundsmith's explanation of RIAA, they backtrack a little and they state that, and I'm quoting here, if one inspects the RIAA EQ, one will discover that there are two areas that occur where a displacement type cartridge will deviate by a small amount from a perfectly flat playback of the recorded RIAA groove, and therefore will not produce a perfectly flat response. That's the end of the quote. Okay, if the two areas that occur are the constant velocity portions of the RIAA curve, this is not a mathematically defensible statement. The 12 dB displacement difference between the bass and treble portions of the curve is not small by any means, and any cartridge that deviates from a flat response by only a small amount in the constant velocity portions of the curve is by definition not truly displacement sensitive. Now, there's a blog on the Audiogon website where he discusses strain gauge cartridges, and he cites my 1996 ARSC paper on disc recording equalization. And he calls my explanation of the RIAA curve wonderful and excellent. Well, that's all very flattering, but it's also baffling since my explanation is completely at odds with the one on the Soundsmith website. There's more on that subject in my linear audio article, which I don't have time to go into today. I'd be happy to send you a PDF file of that article if you want to pursue it further. There's another company in Japan called DS Audio. They make a line of LED cartridges that are displacement sensitive. And this is their flagship model. They have others, including one for 1/10 of the price. And you can see the flagship is over 22 grand, so even at 1/10 of that price, these are not cheap cartridges by any means. Now, on their website, they note that no equalization is necessary except for RIAA curve correction. What that tells me is that their cartridge doesn't have all these other crazy anomalies like the Panasonic strain gauge cartridge that need to be corrected. All that need to be corrected is the RIAA equalization. And they point out that the equalization required for magnetic cartridges must operate over a far wider range than the RIAA equalizer for displacement-sensitive cartridges. And this is absolutely true. If you look at the RIAA playback curve and what the phono preamp with its equalization network is expected to do, the RIAA playback equalizer for magnetic cartridges operates over a range of close to 40 dB, which is no mean feat. It's a challenge to design a phono preamp that will have low noise and won't overload and all of that with this 40 dB operating range. It's quite a technical challenge, actually, from 20 hertz to 20 kilohertz. An RIAA equalizer for displacement-sensitive cartridges operates over a range a little over half that, about 21 dB. So DS Audio is absolutely right about that. And when I was working on the linear audio article, I contacted them to ask about the equalization issue, and I explained my own findings on the subject. And I received a very nice reply from their chief engineer, a gentleman by the name of Hamaguchi Kazuo, and he said that their findings were exactly the same as mine. And I quote his letter in its entirety in the linear audio article. I won't read it all here. And of course, I was happy to hear this, but it also left me scratching my head. How could two manufacturers of displacement-sensitive phono cartridges have such diametrically opposing views on the equalization issue? So, what on earth is going on? I have a theory, which is completely unproven, of course, but I'm going to share it. This is slide 30, yes. Remember that the Panasonic strain gauge cartridge had a rise in response above 10 kilohertz, and that's shown in their patent once again. It's possible that all strain gauge cartridges have a rise in high frequency response, but that others may begin lower than 10 kilohertz. And this may be due to electrical reasons, and it may be due to the cartridge's internal capacitance. These cartridges use, again, a piezo-resistive semiconductor. All semiconductors have a small amount of internal capacitance, in addition to doing what they're supposed to do. And it may be possible to design a strain gauge cartridge to begin rising at a convenient frequency. So let's say, for argument's sake, that a strain gauge cartridge begins rising at 500 hertz instead of 10 kilohertz. This would take care of T4. Now, the input coupling capacitor and its load form a high-pass filter, which would take care of T3. Now, you have to have an input coupling capacitor, or you have to have a coupling capacitor somewhere, because the strain gauge cartridge requires a DC bias voltage. That bias voltage is applied to two resistors, a fixed resistor and that piezo-resistive element whose resistance is changing, okay? Creating a voltage divider. Because of the DC bias voltage, you have to isolate that DC bias voltage from the output of the preamp somewhere. And you can do it with an input coupling capacitor, which will take care of T3. Now, if we add a low-pass filter at the output, that would take care of T5. Now, a low-pass filter will normally roll off the high frequencies above a certain point. But if we apply that low-pass filter to a response that's already rising, instead of rolling it off, it will shelve it. And that'll take care of our T5 response. So that's a possibility. But the question is, what would cause a strain gauge cartridge to have a rising response in the high frequency region? Let's take a look at the front end of the Panasonic strain gauge preamp and its strain gauge element, and this may help to explain it. The schematic on the left is basically it's one channel of the first stage of that Panasonic strain gauge preamp. I mentioned earlier that that elaborate equalizer ahead of it was a flat preamp with a gain of 22.5 dB. This is that flat gain stage that's ahead of that elaborate equalization circuit that we looked at earlier. And you'll note that Panasonic configured this circuit as an inverting amplifier, which is fine. The rest of the examples I'm going to show are also configured as inverting amplifiers, and I'll mention that from time to time. Now, as I mentioned earlier, the actual strain gauge element is a piezo-resistive semiconductor. Panasonic actually referred to their cartridges as semiconductor cartridges, so I know that's what they used. The resistance through the element changes by a small amount, again, as stress is applied. And in the Panasonic schematic, they simply show this element as a voltage source. In my illustration on the right, I'm showing it as a variable resistor. So Panasonic's voltage source, think of it as a variable resistor, and the resistance changes again as you apply stress to the element. Now, semiconductors, as I mentioned earlier, also have an inherent internal capacitance. And this may provide the answer to this question. And that capacitance will be in parallel with the resistance. Now, again, what I'm about to suggest about how strain gauge cartridges might work is an unproven theory. It's an educated guess at this point. Hopefully, somewhere along the way, manufacturers of these cartridges will come clean about how their cartridges really work and either confirm what I'm telling you or blow it out of the water. Either way, I would really like to know. But with nothing else to go on, we'll go with this theory. Again, the schematic on the left is it's the T4, T5 portion of the equalizer circuit for displacement-sensitive circuits that or displacement-sensitive cartridges that we looked at a little while ago, the one that I had worked up. And the one on the right is the Panasonic strain gauge preamp. And as you can see, this resistor and the cartridge look a lot like this circuit here. Okay? They look pretty much identical, except that this one has a variable resistor. The piezo-resistive element in the cartridge and its internal capacitance actually form part of the filter, okay? Now, some preliminary calculations that I did would indicate that, that the internal capacitance in a piezo-resistive semiconductor may be too small to produce a rise at 500 hertz. And if that's true, all you need to do is add a parallel capacitor to this one, and you could do it inside the preamp, right here, or you could actually put it in the cartridge itself. Now, Panasonic probably didn't add any parallel capacitance, which may be why their cartridge's output began to rise above 10 kilohertz instead of 500 hertz. Now, some of you are probably thinking that the variable resistance will actually change the F4 frequency. You're absolutely right. That is true. It will change the F4 frequency by a small amount as the element is being flexed and the resistance changes. So dynamically, it can change. Not by a lot, but by a little. But Soundsmith has admitted that absolute RIAA equalization was not their goal. And in one of his reviews in the Absolute Sound of the Soundsmith strain gauge cartridge and phono preamp, Tony Cordesman quotes Soundsmith as saying, "We are typically plus or minus 1 dB from 50 hertz to 12 kilohertz." Okay? That's quite a contrast to what we normally try to achieve in high-end preamps for magnetic cartridges. And the best of these are usually flat from plus or minus 1/10 of a dB across the entire spectrum, from 20 hertz to 20 kilohertz. Now, you may also be thinking, what about T3? Well, all we need is a high-pass filter for T3, which, as we looked at earlier, is simply made with a coupling capacitor and its load. And this looks just like the T3 portion of the preamp for displacement-sensitive cartridges, again, that I had worked up earlier and showed a while back. And again, we need a coupling capacitor at some point anyway, because we have to block the cartridge's bias voltage somewhere along the way. We don't necessarily need to eliminate it before the first stage, but we need to get rid of it before it substantially affects headroom in subsequent gain stages, and we certainly don't want it at the output of the preamp. What we have here are 2 inverting stages, and so that results in an output that maintains absolute polarity, which some of us think is important. Not everybody agrees with that. Now, here's an alternate method for T3, which incorporates the capacitor into a single-stage preamp, basically into a composite network. And some preliminary calculations I did would indicate that this can work. The preamp inverts absolute polarity, however, but that could still be corrected in a second inverting stage. Now, again, this is just a theory about what might be going on. And unless manufacturers are more forthcoming about how their products really work, it's going to remain just that. It's going to remain a theory. Here's an interesting cartridge, which some people loved and other people have made many disparaging remarks about. I never owned one, I never heard one, So again, I'm not going to make any statements about how well it worked, but I will tell you how it worked. Microacoustics called the vibrating element an electret, but the generator was actually a piezoelectric ceramic element. That's according to Roger Russell. Roger Russell was a longtime engineer for Macintosh Labs up in Binghamton. And Roger Russell has an incredible website that is full of fascinating information on audio history. You can spend hours, days, weeks there. If you have the time to spend, I highly recommend it. You'll learn a great deal, as I have. Now, this cartridge was displacement sensitive, but if you look inside the cartridge right here, you'll see this small board that has 4 passive components on it. I don't know what that little thing in the center is, but it's not connected to anything, so I'm going to ignore it. That was basically a displacement to velocity converter, and it made the output compatible with a moving magnet phono preamp. It basically converted the displacement sensitive output to a velocity sensitive output like a magnetic cartridge, and any two resistor, 2 capacitor network like this for converting the frequency response will also have a 40 dB insertion loss. And that will bring the high output of the ceramic element down to the level required for a moving magnet phono preamp. Microacoustics, I read somewhere, claimed that this passive filter was accurate to within 1/10 of a dB from 20 hertz to 20 kilohertz, which, if that's true, that was pretty good. This cartridge, again, had kind of a cult following. I know some people who owned it who thought it was a very good cartridge. Again, I have no firsthand experience with it. Now, before RIAA defined the modern LP playback curves with 3 time constants, we all know, with the 3 time constants that are familiar to all of us, the base turnover, and that's F4, was normally specified by frequency. The treble preemphasis in record was normally specified by the amount of velocity boost at 10 kilohertz, and the treble playback for magnetic cartridges, in other words, velocity-sensitive cartridges, was specified by the amount of attenuation at 10 kilohertz. And preamps made for archival playback have multiple switch positions to select various levels of attenuation at 10K. But this has generated some confusion. Some people assume that the corner frequency is the same, and that's the rate of attenuation that changes. So you get a bunch of curves that look like this. As you have greater and greater attenuation at 10K, the roll-off becomes steeper. That absolutely is not true. Nearly all the recording and playback curves used on pre-RIAA records, with only a couple of exceptions, they're made with 6 dB per octave filters, which we call first-order filters. And they all boost and record, and they cut in playback at the same rate. So what basically changes is the transition frequency. So instead of doing this, our variable phono equalizer actually does this, okay? It just shifts the transition frequency up and down. The lower the transition frequency, the greater the amount of attenuation at 10 kilohertz. Now, if you're going to design filters to provide variable treble roll-off, or if you're simply curious what turnover frequencies correspond to various levels of 10 kilohertz attenuation, this chart will help. Again, if you ask me for the slideshow, you'll have a copy of it. This shows the most common 10 kilohertz attenuation levels that are needed for vintage disc records and the corresponding transition frequencies and time constants. Now, over 20 years ago, one of my fellow writers for Audio Express and its predecessors, a gentleman up in Liverpool near Syracuse named G.R. Kuntz, provided me with a formula for doing this calculation, which I found that I could not live without. And you know, the formula is a little cumbersome to work with. You don't really need to worry about it. I made a spreadsheet to do the calculation, and if you want to play with it and do your own calculations, I'll be happy to send you a copy of the Excel spreadsheet. You can plug in the decibels of attenuation at 10K, and it'll give you the turnover frequency. And if you want to play with the math, well, you're free to do that too. Not being a mathematician, my main interest is getting the answer and not going through the process. But going through the process is something we all have to do at one point or another, and hopefully the spreadsheet will minimize the pain once you've done the work. Now, there are rumors floating around the internet and elsewhere that RIAA playback equalization destroys phase. And I've read a couple of comments to the effect that since strain gauge cartridges don't require any RIAA EQ, they're somehow better because RIAA equalization messes up the phase response. I don't know where this stuff comes from, but it is complete and total nonsense. The frequency response at the output of a phono cartridge is a result of analog filters. Those filters include the disc cutter and its characteristics and the cartridge, all of which behave like analog filters. And what comes out of the phono cartridge not only has an inherent frequency response, it also has an inherent phase response, but we never have to think about it, okay? But it's there. What this slide shows is simulations I ran on the phase response for the RIAA record as played back by the magnetic cartridge and the RIAA record in a magnetic phono preamplifier in the RIAA equalization circuit. Okay? Curve A is the recording curve. In other words, that's what comes out of the cartridge when you play the RIAA record. And curve B is the complementary playback curve. That's the phase response of the phono preamp. And basically, what you get here, the result is basically a uniform phase, or what you might think of as a flat phase response. Now, the playback RIAA filters in your phono preamp, they are analog filters, and when they apply the complementary frequency response, they also automatically provide the complementary phase response. You don't need to worry about it. The correct phase response comes along for the ride. We don't need to think about it. So if the playback filters provide the correct frequency response, they will also automatically provide the correct complementary phase response. Now, I haven't plotted the phase response of a displacement-sensitive cartridge, but proper playback EQ should provide the complement of whatever comes out of the cartridge, whatever that may be. If it does, the phase response will be correct. Now, some of you may remember way back in the old days, phono cartridge reviews from decades ago in Stereo Review done by Julian Hirsch, an audio magazine done by Len Feldman. You may remember phono cartridge reviews where the old CBS Labs test records actually had square waves that you could test the cartridge with. And they would run them and they would print the square wave photos of various cartridges in their reviews. And surprisingly, reproducing a square wave, first of all, cutting a square wave in the test record, it's not as bad as you might think because of the inherent record equalization, but actually reproducing a credible square wave is not an easy thing for a phono cartridge to do, but the best of them were pretty credible. You absolutely cannot get accurate square wave response off a test record without proper phase equalization. Providing the correct frequency response alone won't do it. The phase response also has to be the complement of what comes out of the cartridge, okay? And again, fortunately, the analog filters in an RIAA network, they do this, the phase response automatically. It comes along for the ride. We don't even need to think about it. So far from destroying phase, an accurate RIAA phono preamp actually restores correct phase. So that all that nonsense about RIAA equalization destroying phase, it's exactly that. It's just nonsense. So that is the conclusion of the main part of my presentation. I have some more slides I can show you, but I think this is a good time to pause for questions. Bob.
Hold on. Bob. You gotta get this
The microphone.
Can we make it?
I've seen software that has existed that provided equalization using digital means, and it's my understanding that in some cases they may not have gotten the proper phase response in the equalization. Is that true?
I'm glad you asked that question. Everybody hear that? You can do phono equalization, playback equalization digitally on your workstation, on your computer. And Bob says it's his understanding that some of those plugins may provide the correct phase equalization and others may not, and he's absolutely right about that. I gave a paper quite a number of years ago at one of the national ARSC conferences on phase equalization and its importance in the reproduction of disc records. And I explained how the whole phase equalization works, how it comes along for the ride with analog playback filters, and why or at that time, I gave this, it was quite a number of years ago, a lot of the plugins for digital workstations didn't provide the correct phase response, and I showed some square wave photos that I captured off a scope with several programs that I had tried, some of which did provide the correct phase response and others which didn't. Whether it's due to my paper or not, most manufacturers that have plugins now for doing phono equalization digitally seem to have addressed the phase issue. But the only way you're going to know is to ask them. I asked several manufacturers of digital equalization plugins if theirs did, and some told me they didn't know. You know what? If they don't know, don't buy it. And others told me, yes, they do. The one that's made in New Jersey, DC-10, I think it's up to now, they have what's called a virtual phono preamp, and it does provide correct phase equalization, and it gave correct square wave response when I tested it. I think its predecessor was DC-6 or DC-7 at the time, but it did work right. I tested some others that didn't work right. So you need to ask the manufacturer, and if you're ambitious enough, you can actually record some square waves. The best thing to do is do it don't try to record a 10 kilohertz square wave at a sample rate of 44.1 kilohertz because it just won't work. Do it at 96 or 192, look at the results on a scope and see if the plugin works properly. But that's a really good question, and the answer is now more manufacturers seem to have taken it into account and have done it properly, but I can't guarantee that all of them have. And again, if they don't even know the answer or don't even know what you're talking about, look elsewhere. John.
I'm holding the mic. Back to your Panasonic strain gauge cartridge. But Panasonic is, of course, a mass marketer. What's the advantage of designing that? It would require a unique phono preamp in all their equipment that use that cartridge. Why would they do that? What's the advantage over a regular magnetic cartridge?
It's a really good question. The people that like strain gauge cartridges seem to think that they have better transient response and more detail and actually have lower mass than moving a magnet. Again, there's more than one way to design a transducer. It's another approach. I don't know that it's necessarily better or worse, but everybody that's listened to strain gauge cartridges, I have not, will tell you they do sound different from magnetic types.
Can't you probably find one of the Panasonics for not a fortune? I mean,
You can find the Panasonics on the internet. They seem to go for quite a bit of money. If I could get one cheap, I would take it apart and try and find out. In fact, Tom Fine, who some of you know, who's a good friend of mine, Tom Fine asked me, why don't somebody buy one of those Soundsmith cartridges and take it apart and see how it works? And I explained to him, because he didn't realize that the cheapest ones were about $9,000. And I told him, if they were $300, I would buy one and take it apart, or I would at least measure the capacitance at the output terminal of the cartridge to try and figure out what's going on. But at those prices, no, I'm not going to do it.
Or just listen to it and see what it sounds like.
Well, you could listen to it, yeah. You'd have to buy one. So, other questions? Seth, did you have a question?
Yeah. Take the mic.
Go ahead, yeah.
What do you like to use?
All right, what do I like to use? I thought
Yeah, by the way, you were talking about all that with the phono. You remember how I struggled over that at the beginning, trying to create that without the phase correction?
I know.
Adrian Cosentini tried the same thing with another digital program.
Yeah, related to Bob's question. Yeah, I talked to Adrian. The year I gave that phase equalization paper at ARSC, Adrian Cosentini, who used to be the chief engineer up at the R&H Archives, Adrian said to me, years ago I was working on a project, and I tried applying the phono equalization digitally. And he said,
Me too.
he said, I couldn't quite put my finger on what was wrong, but it just didn't sound right. Well, and then he realized the problem probably was that the plugin he was using to create the playback curve did not provide the correct phase equalization.
It didn't have the correct phasing, but it also had a problem of trying to get the your T3, your T4. You couldn't recreate it properly. You couldn't get it accurately. You'd play with one filter, you get the frequency in right, you play with another, all of a sudden that frequency went off.
Interesting. Well, again, it
Yeah.
depends on the plugin. And again, I think now they're a lot better than they used to be, and most of the manufacturers are taking those things into account. Yeah, people sometimes ask me what I play my records on, so I actually took a few pictures, and I'll show you what I do. This is a turntable that I built. I do a fair amount of do-it-yourself audio. It's a turntable that I built, which is a belt drive turntable that's actually based on the old ARXA drive system, which is a kind of a classic turntable from the 1960s that had a drive system that, although it may not have been implemented with the utmost precision, and the tone arm may not have been the most elaborate in the world, it was a principle that was fundamentally right. And what I did with the AR turntable is I basically wound up with a turntable that used only the platter from an AR turntable. I designed and built my own base for it. This frame around the outside is 7/8 inch solid oak. I have an 1/8 inch thick aluminum top plate and double thick 3/4 inch high density particle board that's epoxied and screwed to this top plate, except for a cutout for the subchassis. And what I have in this turntable, I started out by trying to modify the old AR aluminum subchassis, damping the resonances and so forth, and modifying the back end of it so I could mount different tone arms on it. But it was kind of a stopgap. And in the mid-1980s, I hooked up with a gentleman down in Tennessee by the name of George Merrill, who's a pretty well-known turntable designer and is still building high-end turntables. George Merrill was making modification parts for AR turntables. And what I wound up doing was using Merrill's acrylic subchassis, his bearing and his spindle. And he also did a lead coating for the platter, and he balanced the platter just like you have your wheels balanced when you get new tires on your car. You had a little mark on the inner and outer platters that you lined up for proper balancing of the platter. And I also have George's rubber cork compound platter mat. This turntable also has Merrill's high torque synchronous motor, and I have a pulley and a belt that I bought from an internet company called Vinyl Nirvana, which are both very, very good. The tone arm is a Gelco SA750. This is the SA750D, which is the shortest version of that arm that they made. They had 3 different lengths, and I'll get to one of the others a little bit later on. So that's the basic turntable. The cartridge in here when I took this photo, was a Grado Signature XTZ2. It's a cartridge that was the top of the line Grado cartridge in the early 1990s, and Joe sent me one to try, and I used it for a long time. I found it to be very, very good. I like turntables with 3-spring suspensions. Basically, the subchassis is suspended from the turntable top plate with 3 springs, which isolates it from acoustic feedback and so forth. Suspended turntables, for some reason, have fallen out of favor. Most turntables that are at least affordable ones, even turntables that cost thousands of dollars, a lot of them do not have a suspension. And they rely on things like sorbethane isolation feet and like that to isolate them from vibration. One of the issues that everybody that works with suspended turntables wrestles with is the tone arm cable, because tone arm cables tend to be rather stiff and heavy, and you plug the cable into the bottom of the arm and you try to dress the thing properly so it won't interfere with the turntable suspension. It's a rather difficult thing to do, and I finally gave up because it just was very problematic. And I decided I would put a plate on the back of the turntable with a pair of RCA connectors, and from those connectors I would use very thin, flexible Cardus tone arm wiring and a Cardus 5-pin tone arm connector that would plug into the base of the arm. And this ensured that the very flexible wiring wouldn't interfere with the turntable suspension. And then you can hang any old heavy interconnect cable off the back of this thing and run it to your preamp, and it won't interfere with the turntable suspension. That works extremely well. I have 2 ground posts on this thing, one to the ground for the tone arm and cartridge wiring, and another ground post that goes directly to the top plate. And normally they're tied together. I also, back in the mid-1980s, designed a low distortion power supply and speed control for this turntable. Most turntables that do not have built-in electronic speed control, they run on synchronous motors. And the motor speed is basically determined by the AC line frequency. Synchronous motors are designed to be powered by sine waves. Has anybody ever looked at your AC power line? It's a horror. Don't ever connect an oscilloscope directly to an AC power line. Do not do this, okay? What you need to do is you need to have an AC voltmeter with a 300 volt scale or a distortion analyzer with a 300 volt scale. And most voltmeters, AC voltmeters on the back will have an output that you can feed to a scope, and a distortion analyzer will have the same thing. That's the proper way to look at it, to do it without blowing up your oscilloscope and without electrocuting yourself, okay? You have to be very, very careful, but that's what you need to do. Never, ever connect the scope directly to the power line. But if you look at the AC line, you find that it's not a sine wave. It's supposed to be, but it's clipped. There's flat topping in virtually everybody's power line. And the flat topping is caused by all the nonlinear loads that are connected to the AC line in your house and in your neighborhood. And those nonlinear loads are refrigerator compressors, computers with their switching power supplies, all kinds of nasty stuff that basically throws energy. It's all reactive, and it throws energy back onto the AC line. Synchronous motors don't like clipped waveforms. So what this thing does is it provides a pretty low distortion, about 0.5%, pure sine wave to the turntable. And I've talked to people who built this thing, because I wrote an article about it about 35 years ago. And I've talked to people who built it and said it made every synchronous motor turntable they tried it on sound better. And it does. I have basically a low distortion oscillator. It's based on an XR Corporation function generator chip that isn't even made anymore, but I'm well stocked in case I need replacements. The output from the function generator goes to a small power amplifier, and from there to what is essentially a filament transformer wired backwards, 12 volts in, 115 volts out, and that's how I get the proper voltage for the turntable. This is an absolutely invaluable asset. And because in terms of getting the best performance from a synchronous motor turntable, I wouldn't be without it. And most belt-driven turntables that plug directly into the wall, they don't have a pitch control. Well, I can vary the oscillator frequency here, and I have a very wide range of speed adjustment, because synchronous motors, again, their speed is determined not by line voltage, but by the frequency. And so by changing the oscillator frequency, I get variable pitch out of this too, for correcting transfers on LP of old recordings that have been transferred at the wrong speeds. And of course,
What
many of you
percent?
know
What's the max and minimum percentage you can go from center point?
Well, the thing is, since this has 33 and 45, whoops, I did not want to do that. We just lost it. I think what happened is I left it up on one slide for too long. At any rate, since this thing has 45 speed, if you want to get, with the 78, with this, oh, thanks, yeah, that's fine. Let me go back to, whoops, to where I was here. If you have this thing in 33 1/3 speed, you can get this thing between 45 and 33 1/3. They'll overlap by a point where you can get plenty of speed adjustment out of it. This has a 33-45 switch, which is again accomplished by changing the oscillator frequency. The old AR turntable, you had to take the outer platter off and move the belt from one pulley to another. You don't have to do that with this. I originally had a frequency that was correct for 78s, but I found that these synchronous motors in belt-driven turntables won't turn that fast. They simply won't run, so I scrapped it. But you can get plenty of range of adjustment out of it.
In other words, to play LPs and 45s.
Yes, absolutely. Okay. Phono preamp. My main preamp up until fairly recently has been, it's been my own preamp in an Adcom GFP 565 box. I basically reworked it entirely inside. There's a fair amount of Walt Jung's design work inside it, plus a fair amount of my own. And this is the phono preamp. It's a feedback-based RIAA phono preamp that I did within the confines of the old Adcom phono preamp footprint. It's DC servo controlled, and that's what this board is here. It's a DC servo board that sits on top of all of this and is connected with short lengths of wiring. It eliminates the need for a coupling capacitor, the servo controlled. It's a very good preamp. I now use a Denon DL103R low output moving coil cartridge, and I built my own step-up transformer with a pair of Jensen moving coil step-up transformers, and which I mounted in this small project box that's made by Hammond Corporation. There are moving coil step-up transformers that cost thousands of dollars. I built this thing for about, I don't know, $250 or $300. It works very, very well. I'm not going to say it's going to compete with one that costs 10 grand, but I think it performs extremely well. That's for LPs and 45s and like that. This is my 78 RPM, or actually I should say it's my turntable for any vintage material, any pre-RIAA material, whether 78s or lacquer discs or LPs that are pre-RIAA. It's a Techniques SP15, which a lot of you will be familiar with. This is the longest of the Gelco SA750 tone arm. This is a 750L. According to my measurements, I could actually sneak a 20-inch Pathé record onto that turntable. It should just about fit.
Is it a 12-inch?
I don't own any of them, so I haven't been able to try.
Is it a 12-inch arm?
Yeah, exactly.
And if you
yes.
could set, if that's set properly, it will play a 20-inch with no problem.
According to my measurements, one will fit, just barely.
Yeah, then you're okay.
I haven't had a chance to try it.
Yeah.
My approach to setting tracking force is not to simply stack coins on top of it until the stylus plays in the record. That nickel is required because I can't get enough counterweight adjustment for the 7-gram tracking force I use in the Stanton 500AL for playing 78. So it's all part of the equation, okay?
Right,
and it has been measured.
Yes, but it also adds mass to the head shell a little bit.
Yeah, which isn't a bad thing for those Stanton cartridges because they're fairly non-compliant.
Yeah.
They have fairly low compliance.
You're using 7 grams to play 78s most of the time, is that right?
Yeah,
Do I
that's
what
what
now?
that's what the
You're using
stand.
7 grams to play 78.
7 grams.
Yes,
yeah.
most of the time. And I found, and Seth has found the same thing. If you've got records that are at all warped,
Any sort of fast
lower
warps.
tracking forces, it's a nice idea, but it just doesn't work on a lot of old vintage material.
If you've got a cartridge in there, like if you're using the higher compliant Shure assemblies,
They won't do it.
you cannot play a fast warp. A warp going, a record that has a fast warp and it running at 78 RPM, the whole tone arm will start to shimmy on you.
Audio-Technica has a new line of phono cartridges. It's ATM or ATM something 95. It replaces the old AT95 cartridge. And they make the cartridge with a bunch of different styli, including a regular 3 conical 78 RPM stylus, and you could have it re-tipped. Their cantilever will go up to 5.5 grams. I ordered one on Amazon and tried it. And the cantilever, the stylus, is so close to the cartridge body that on warp records it bottoms out.
Yeah. No, you're
So I sent
hitting
it
its
back.
max.
I mean, you could send it away and have it re-tipped if it worked right, but it just...
No, there
the
was.
500AL was not an expensive cartridge back when it was made. It's
but-
not a high-end audiophile cartridge, but it's pretty decent. There are
Yeah.
better cartridges out there, but
However-
the thing is, we have a lot of styli that were once available for the 500AL. Seth
Well-
has got about 50 of them. I've got about 8
Yeah,
of them.
well, the
And,
thing was, yeah.
Getting decent truncated elliptical and truncated conical styli for any cartridges now is a very difficult proposition.
Mm-hmm.
So Seth and I have both stuck to the 500AL because we have all these stylus assemblies
Well,
that are available.
there was something else too. Tom Owen came up with that 500 AL cartridge. That was a special design he worked out with Stanton. See, their standard, they didn't do it for the 500. What the heck did they do it for? The one with the blue dot on it. Which one was that?
That was for the 500 AL, but it was...
Oh, you're right. It was their 78, but that one had a cantilever that was higher compliance, and it only took a weight of about 5 grams. Tom had them make that cantilever thicker, and it also is slightly longer. Your overhang has to be
it is
readjusted.
longer than their stock 78 cantilever.
It's not the
yeah.
same. It's not the same replacement stylus that you got from Stanton.
No.
He knew what he was doing when he went to them with that.
Well, he worked with George Alexandrovich, who was the
Sandrovich.
chief engineer at Stanton. And
Yeah.
Alexandrovich actually designed the stylus according to his specifications.
Specifications. He did a modification. He saw the problems. And those styli, I tell you, I've got over 50 of them back 30 years ago when I used to play positives from BMG. They tracked, metal parts that had little fast warps in them very, very well. And there was something else that he came up with, that George came up with, that nobody could figure out. He came up with the biradials to play stampers and masters that go backwards. And I had the brains enough that when I had to do work for BMG at the time, I was in Brooklyn, I drove out to Plainview. I said, give me every size you got. I grabbed seven different sizes, so I have everything to play from micro groove up to coarse groove acoustics. And I had an SP15 modified to go backwards, and I found the one head shell, an Autophon, that I could mount the cartridge in backwards. I made the wires and the connectors, and then I went to SME. I said, make me a better set. And I was able to put it in backwards, and using the protractor, I was able to move the overhang of the arm. And in fact, I just got a call from, who is it, Graham Newton, that he has some LP metal parts he wants me to transfer. And it's like, I'm one of about, I think, 3 people in the country that can do that. But everything was done at a time. This was all archival work. And it worked. Ideally, my idea is to try to find a manufacturer that would listen to me. I'd love to take the V15 Type 5 assembly, but make it with that, stylus grip in it. So it's give you the extended frequency response, but with the lower compliance so you could play problems with fast warps, and come up with one that was slightly higher compliance, like the N111 that was used for the 78s, which you can use on lacquers, slow speed lacquers to play them perfectly.
Let me continue, because
Yeah.
we need to be done here at 9 o'clock. So let me
Yeah.
just finish up fairly quickly. This is my own archival preamp that I built. I gave a presentation on it in this very room back in 2012 in the early days of the New York chapter. It has 12 different bass turnover frequencies, one of them being flat with no turnover frequency, 12 different treble roll-off rates, including flat. It has polarity inversion in each channel, so that's how you do the lateral vertical switching. It has a mono switch, a stereo mono switch, a mix balance control that you can adjust the mix of the 2 groove walls. It has an external processor loop that you can go out into an external equalizer or other signal processor, and it has a switchable rumble filter. And it has balanced inputs and outputs, as well as unbalanced for the main ones that you're most likely to use. This is the inside of it. It's probably the most complicated thing I've built from scratch. I have a flat phono preamp. I have an input buffer circuit because you can go into the phono equalizer line level as well. This is the phono equalizer. All the switching of the equalization circuits is done with relays to avoid these lengthy wiring to a front panel switch. All the front panel switch does is turn the relays on and off, so it means very, very short wiring distances to the active circuitry, all of which is op amps. This is the line stage that does the lateral vertical switching and the rumble filtering and all of that stuff. Power supply regulators, separate power supply regulators for the phono section and the line stage. A separate power supply regulator for the relay supply. I got carried away, but I think it's the right way to do it. And I have little boards that I built here for the balanced inputs and outputs that are based on that corporation's balanced input and output chips that I think are quite good. And this is the wall wart, if you will. I don't like wall warts. This is a really high current outboard supply that has a real power transformer, rectifiers, and raw supply filter capacitors, so that no AC from the line goes into this thing. What goes into it is unregulated DC. And separate transformer and separate rectifiers for the relay supplies. I kept it completely isolated. And that's pretty much it.
Oh, you remember the first time you brought it down to my studio? What
Yeah,
happened?
he wouldn't let me. He wanted me to leave it. He tried to trick me into leaving it with him. You can't have
I
it.
almost tried to lock him out of the house and say,
At any rate, that's the show, and if you want copies of the handout, the slideshow, any of my articles that are listed there, just drop me an email. I won't be back in town until the first of next week, but be happy to send them to you. John?
In a prior program, you played us the Caruso record, you could get dubbed
Yes, I did.
using your RIAA.
Yeah, when I did that presentation back in 2012, Seth and I transferred a bunch of things and played some examples of what the preamp sounded like and so forth. So, any other questions? Well, thank you all for coming. It's been fun. Thank you,
Gary,
sir.
as always. By the way, before you leave, you're not allowed out of this room until you answer his quiz. You're going to be handed a set of papers by him. Anyway, this is the end of the April meeting. Our next meeting is going to be on May 16th, a month from now. It will be the week we all come back from ARSC, which is going to be in Portland, Oregon. It should be an interesting conference from what's posted on the website concerning the programming. And our presenter next month is going to be Gilda Miros, and her title of her program is going to be called The Golden Age of Latin Music. And if I'm correct, Daniel Cordovez, who's a member of ARSC, who is staff on Rogers and Hammerstein archives at the library, may be introducing her. So tune into next month, and I'll see you when we get back from Portland. Have a good evening, everybody.